Okay, here's another dynamics problem for you. Let's say we have a block of mass m sitting on a table, and there is friction, and it's connected to another smaller mass of 2 kilograms that is suspended by a massless cord that is over, let's say, a piece of smooth glass, so that there's no friction and there's no mass in that cord. We're going to release the little mass from a height of 1 meter above the ground, and it will accelerate downward. And what we want to know is, given this information, what is the value of the big mass? There's also friction between the big mass and the table, and the coefficient of sliding friction in this case, mu, is equal to 0.2. The acceleration due to gravity is equal to 9.81 meters per second squared. So how do we set this up? Well, first of all, let's look at the forces acting on the system. On this mass right here, there's the force due to gravity acting in this direction, which I'm going to call mg. And there's the force of tension that's in the cord here, back up that way. But that's also the same tension that is pulling on the big mass, so that's an internal force pair. Force due to gravity acting on the big mass is like this. And as I said, there's friction between the mass and the table, so there's a force in this direction, a little f that we'll call the frictional force, and the force that the table exerts on the mass m, which is up this way, and that is the normal force, F sub n. So when I let this go, it falls, and it takes a time of 2 seconds to cover this distance h of 1 meter. So from that we can figure out what the acceleration is, and we'll leave that for a moment. Let's set up the equation that it's going to take to find out what m is. And also, by the way, we want to find out what m is, and we want to find out the tension in the cable. So what we have is little mg pulling in this direction, and we have little f, the frictional force, pulling in this direction. Those are the only two forces in this dimension that cause this system to accelerate. So we can write Newton's second law as the net force, F net, which is little mg minus the frictional force, and that's equal to ma, but m includes the little mass and the big mass, so I'll have to add those up. Little m plus big M times a. So the frictional force, little f, is equal to the sliding coefficient of friction times the normal force, so that's equal to mu times, well, the normal force is just equal to the weight, mg, like that. So I can rewrite this equation as mg minus mu times big mg is equal to little m plus big M times a. And then I'll just solve this equation for big M. So let me write it like this. Little mg minus mu big mg is equal to little m a plus big M a. Now I'm going to move this to this side and this to this side, and I'll write this then as m times g minus little a, moving this one over here and this one over here, means that big M times a plus mu times g, it goes on the right hand side. And then if I divide both sides by this term, I get that m is equal to little m g minus a minus, divided by A plus mu times G. And that's how I'm going to find out what big M is. But I need to know what little a is in this, because I know everything except little a. So a I can get because I know that h is equal to 1/2 a t squared. And that means then that a is equal to 2h over t squared. And that is equal to 2 times 1 meter divided by 4, which is t is equal to 2, so that's 2 squared, and that's equal to 0.5 meters per second squared. So that means then that m is equal to little m, which is 2 kilograms, times g, which is 9.81, minus a, which is 0.5, divided by 0.5 plus mu, which is 0.2 times 9.81. And when you stuff all of that into the calculator, you get 7.56 kilograms. 7.56 kilograms. That's what one of the things that we were looking for. We also want to know what the tension in the cord T is, but we have an equation that we can write just for this particular mass to make it really easy. And let me push it up just a little bit here. And since little m is bigger than t, rather little mg, that is, mg minus t is equal to little m times a. And then this means that t is equal to m times g minus a. I move this to this side, that to the other side. T is equal to m, little m, times g minus a. That's equal to 2 times 9.81 minus 0.5. And that works out to be 18.62 newtons. 18.62 newtons. And that's what the tension is equal to.